Thanks for the introduction, Usman. I'm going to talk about power management of Exascale networks using the runtime system by some new hardware features that I'm going to introduce. So this is the fourth talk this morning about power. So you should be pretty convinced that power is a challenge, if not the major challenge. Power, for instance, Blue Waters is consuming up to 13 megawatts, which is enough to electrify a small town. And it takes all the power and cooling infrastructure. If you want to build something bigger than that, for current technology, good luck, because you are not going to have that infrastructure for a single building easily. It is projected that 30% of the power will go to the network for future machines. I don't have the breakdown for current machines. There is this work from Sandia National Laboratories. They took this Cray XT cabinet and changed the configuration. They did all sorts of things that needed, like rebooting the system, administrative accesses, all those things. And they saw 25% power decrease when they turned down the network to its lowest configuration, less bandwidth, all sorts of things. So this 30% is not totally unrealistic. By the way, this is projected by Peter Kagi. This is his design in the Exascale report, DOE report. So network is different than the processor. Network is not energy proportional. This is the term which is used recently. It means that the network is near its peak most of the time. So if you have, so the consumption is not related to the utilization at all. Unlike the processor, as you saw in the previous talk, during communication, the processor was consuming less because it was almost idle. A lot of work has been done inside the processor for like power gating, changing the configuration so you consume less when you don't have workload, you don't have much floating point operations. But in the network, there hadn't been much work in that. There had been some recent studies to address this issue. Just for illustration, there is a work from Google at ISCA 2010, which shows that 50% of the data center's power can go into the network when the processors are underutilized. This is for non-HPC data centers, so this isn't illustrative for HPC, because in HPC, hopefully, we are not going to have underutilized CPUs as much. But this is for showing the point that networks are on all the time. It is said that 65% of the network's power is for the links, because the links have to send signals all the time and be ready for communication. So we are going to try to address this issue, that 65%. So what are those networks that we are working with? For Exascale, almost everybody is looking at Dragonfly. Inside the Exascale DOE report, IBM has PERC's network in Power 775 machines. You saw some results yesterday from Extend Talk. In the Extend Talk, Cray has Ares network in the Cascade line of machines. So a lot of vendors are moving towards Dragonfly for several reasons. Other than that, the other big network is high-dimensional Tori networks, 5D Taurus in IBM Blue Gene Q, 6D Taurus in K Computer. These networks have one thing in common. They are high radix. They have a lot of links. The reason for that, I can refer you to Bill Dolly's talks. Why? Because he's the expert in interconnection networks. He explains why the technology is going that way. It's better than having like high bandwidth, low, but less number of links. So these are the networks. The applications have different communication patterns that map to this network topology. The network is designed for a wide range of applications. So these figures are for two different applications. Milk, which is some simulation code for Blue Waters, and this is NPBCG. So each axis is a processor number. So each dot shows a pair of processors communicating together. For instance, for Milk, you see this around the diagonal, which means that you have a lot of nearest neighbor communication. For this CG, you have a lot more dots in this diagram, which shows that you have more global communication. By the way, this CG is dense CG, I think, inside NPB, which is not very realistic for applications, but this is the worst case that I'm showing here. So when you map those applications to the network, you're going to have a lot of unused links ever during execution. This graph shows a couple of different applications and the number of links that they use from the network. So we have full network, which means that you have every pair of processors connected. This isn't very realistic. This is just for illustration. But if you have like a Dragonfly inside the lowest unit, you have full connection. So it can be applied in small jobs. So you have this red full network. We have the Perks network, which is basically Dragonfly, 3D and 60 Taurus. For the applications, I have two NAMD instances. This one is the more realistic one with the PME option on, which is long-range force calculation. We have a lot of NAMD experts here. You can ask them what this means. But I separated this because PME happens less frequently. It's like every 4 iterations, I think. So we can do something about it. And I'm going to explain later. And we have MILK and some NPB benchmarks. As you can see, the Perks network for these common applications, less than 20% of the links are used, links of the whole Perks network. And the CG is an exception, which uses like 55% of the links, which is kind of like the worst case. For Taurus networks, you have much higher utilization. But when you increase the dimension from 3D to 60, you see that it drops dramatically. By the way, these MG and BT are representative of very common applications with nearest neighbor communication, and they are similar to MILK. So let's move on. To have some simpler benchmarks to play with, we have some nearest neighbor benchmarks we call Jacobi, similar to Jacobi relaxation, 2D, 3D, and 4D. You see that less than 20% of the Perks links are ever used during execution. And for one interesting point is that for 3D nearest neighbor, you have around like 85% instead of 100%, because this 3D pattern is for the cores. If you have like MPI paradigm, not MPI OpenMP paradigm, when you map it to the nodes, you are going to have less utilization of the links. It's even worse when you look at more expensive links. For Perks network that we have more information, we were working on it because of Uluwatu for several years. You have different kind of links. You have LL links, more local links, then LR links, then D-link. These D-links, these links are use electricity. These are optical links. So these are higher cost. These global links across cabinets are higher cost. For a lot of these cases, this blue is very important. Blue bar is very important. Even for NAMD PME, which uses a lot of the links, nearly all of the links, you see that it leaves some of those D links. For common like MG, BT, you see that this is like less than 5% of those expensive links are ever used during application execution. CG is an exception, which uses a lot of them because of the global communication. By the way, I have to emphasize more on this CG because this is the worst case, which is a dense CG. For sparse CG, you're going to have nearest neighbor communication similar to these guys, which is the more common case. So more expensive links are used even less. This is for nearest neighbor. As you can see, only a tiny fraction of the expensive links are ever used during execution. So what can we do about this? We have all the links, a lot of links never used, but they are on consuming power, wasting power for a lot of common applications. People these days talk about the networks as being overbuilt. Maybe that's true, but they have to support the worst case application. For instance, FFT with all-to-all communication. You cannot like sell a supercomputer to NSF without supporting FFT for very important applications. As a similar case, processors are also overbuilt. They have execution units for integers, different floating points. Many of them are never used, but processors manage this power. Networks don't. We have to find a way to make networks energy proportional, just like the processors. We need to consume according to the workload and utilization. So our solution is turn off unused links. This isn't very unrealistic. There is even some commercial network with this capability from Motorola. This machine actually exists, and I'm going to talk about it later. We think that runtime system is the right place to do this power management for several reasons. If you have hardware, actually this problem has been well studied before in other communities, non-HPC communities. That's why I have a couple of related works to look at. Hardware can cause a lot of delays according to some related work because it has a small window. It's going to see there is nothing coming up, turn off the link. Oops, there is some packet, turn it back on, some delay to the application. Compiler doesn't have enough information, obviously, because the data flow is input dependent most of the cases. An application does not know the hardware. This application is going to be running on a lot of different machines, and you cannot expose these information to the science programmers. They just don't understand the topology and network and these kind of things. So runtime is the best because it mediates all the communication. All the communication has to go through the runtime, so it knows the application and it knows the hardware, both of them. And you are tuning your runtime for every machine anyways. So is this feasible? In our community, we focus on production. Nearly all the talks that you heard in this workshop were like about some software or something that you could just download and use it right away. But this is not. You cannot it's not probably available for your cluster downstairs of your department or something. But so we need to convince hardware vendors. We have attendance from Cray and IBM, so we can talk to them. The runtime can give hints to the hardware, and if those hints were wrong, the hardware has to turn the link back on. So there is some small penalty, and I'm going to talk about it. There is some other, so we have to have hardware support for this, and this has been done before, so it's not something weird and totally exotic. We have multiple jobs in a lot of machines. So what's up with that? For instance, in Cray machines, you have interference of different jobs. So if you turn some link off and some other job is using it, it's not very good. You're causing more delays to that job. First of all, isolated allocations are becoming more common. BlueJeans, IBM machines have isolated allocations already. You're going to get a cube of BlueJean when you ask for a job. No interference, you have the network by yourself. For Cray machines, they are doing that. Hopefully for Blue Waters, we're going to have it next year. I don't know if I have to talk about this job scheduler or not. We are trying to convince them we don't like interference. Probably at some utilization cost of the machine. And one other point is that you buy capability machine for big jobs. If you were going to run a lot of small jobs, buy some server farm, low-cost data center just like Google. Why are you paying so much money? So if you do these, if you consider these, some of the software design choices become more important. In a study by Abhinav and Nikhil in this room, probably, at SC, they showed that default mapping in Dragonfly network can have congestion for common applications. They had two solutions with very similar performance, which had a lot of good, good speed up over the default. Random mapping of processes to processors and indirect routing inside the network. We see that the links are nearly all the links are used for indirect routing because you choose some other super node randomly and go through that. But for random mapping, around like 40% of the links are used. So for these software and hardware design choices, I don't know if I have to call this hardware or software. For these design choices, this one is better than the other one in terms of power if you have such schemes in place. So this is just one example. I'm not going to go more into the design choices of the application and machine. So that was for links that were never used during application. That was significant, but we can do more. To see how much more we can do about this, let's have a power model. Because used links are not used all the time. They are used for communication phase of the iteration, usually for HPC applications, when you have like compute, communicate stages. So we want to have a power model for network capacity utilization. What fraction of the network capacity is used? We need some average. We are going to consider average utilization of all the links, assuming that links are turned on and off magically at the right time. When there is some packet coming, the link is on. After that, it's off. We are not going to consider 0 byte packet latency either. And we are not going to consider any switching delays. For instance, when you have like 10% of your network, your iteration time communicating, your network utilization is 10% of the total. So when you apply this model, you will see that for a lot of applications, you are using less than 5% of your PERCS network, even for Tori less than 10%. CG is an exception, which uses like 12% of PERCS and 40% of Taurus, because most of the application is just communication. So only a tiny fraction of the network capacity is ever used during the application execution. So we can schedule these on-off instructions from the runtime system to try to save the power consumption of those links, because the runtime roughly knows when the message is going to come. The iterations do the same thing over and over again for the execution of the application. You know the iteration time is like 10 milliseconds, and after 9 milliseconds, I'm going to receive a message. So you roughly know when it's going to happen in the runtime system. But you need some low noise machine that these iteration times don't change as much, which is, again, related to the interference that I talked about. But IBM Blue Jeans seem to be very good in the experiments. There's a delay for switching the link, but this delay is so small. For the current implementation I talked about, it's like 10 microseconds. They even mention it in terms of the number of cycles in network community. They say like this is 10,000 cycles of 1 gigahertz machine. So it's much smaller than the iteration time. The runtime can also be conservative. Schedule the offs like earlier, actually later. Schedule the ons earlier to make sure that the packet is not gonna have any delay. So it's similar to having more switching delay. So I add this effect to the delay in the graph later. So this is the delay overhead. This axis is delay, link transition delay from on and off, and this is network capacity utilization. If I have more delay, I'm using the link more often for more time period. So around like 1 millisecond or a couple of milliseconds, that's fine. I'm not going to use more of the network, which is but when you get close to the iteration time of some applications, like tens of milliseconds, you are going to have more overhead in doing this. But in this period, note that on the left is 10 microseconds that I talked about. So even if you are conservative and you go to millisecond range, that's fine. You're going to save a lot of network capacity, almost the same. So this is the summary of the results if you apply these techniques. Basic means that you don't schedule, just turn off the links that are never used. Schedule 1 millisecond, which means that you are scheduling with 1 millisecond switching delay and conservative action. And we have results for PERCs and 60 torus. So from the whole machine power consumption, we can save up to 20% if we do a scheduling. If for most applications, if we don't do a scheduling, we can and just turn off the links that are never used.
You're seeing 3% of the energy goes to the network.
Yeah, that's
speculation. So if this is the whole network is 30%, that 10% is for the routers. So we are not playing with that for now. But there is some work for saving routers power. You can look up the literature if you like. So we can save around like 15% of the machine's power by just turning off the links that are never used for these different applications. And that's about it. I hope that you're convinced about the results I have, even though they are based on simulation and these are not very common in HPC community. If you have any questions.
Maybe you said better than me. So you try turning on and off, but you try also with routing, like trying to interact to switch more links.
You mean like routing the messages so that you are not using too much link?
If you think that the bandwidth is low enough that you can multiply from 10 routes and like longer routes,
That's a very good idea actually.
Can you repeat the question?
The question is why don't you reroute the messages to use less links, because the bandwidth might be good enough to multiplex the links. This is a very good idea, and you can apply a lot of similar ideas on top of this. But the thing is, we first need, these results are good enough for the vendors to look at. So we are trying to convince the vendors to implement this. Then we can go ahead and do more to save even more. These results are pretty convincing so far. We should do more research and incorporate things that we talked about into that too. I agree with you.
Any more questions? At least to me it seems that the other side of that coin is to use indirect routing, but use it so that you would utilize more, not fewer, right? Because that's what it's going to lead to according to configured actually. So,
communication is only processor-to-processor communication from messages, right?
Yes.
You don't, but there are machines today that do I/O through the communication network, so that would be a different kind of traffic. You have not analyzed that.
You mean like with adaptive routing and stuff?
No, just when you do I/O, your I/O traffic will go through the network, the same network that is used for inter-processor communication. You haven't looked at I/O at all.
Well, honestly, I haven't looked at I/O. For previous Bluetooth, I think Bluetooth I/O network is separate for some machines. If you do your I/O inside your own partition, I think this still would work. But if like you have interface for I/O, so you have the same performance penalty also, performance interference. So the same thing applies to I/O. I didn't look at very I/O intensive applications, which is another study to do on top of this.
Thank you very much, Ehsan.